Hello everyone, in this tutorial you're going to learn how to simulate a 2D wire bracket in Abaqus. This example is going to be simple, however there are some new elements that you're going to learn for the first time. For instance, how to apply a distributed load or how to use a field function to generate the equation to apply a triangle distributed load. And also you're going to learn how to partition the line to apply a concentrated load at a specific area. So what we have here, we have three fixed area, and as you can see all the units are in meter, so we're going to use a meter SI system. And so because we are using a 2D wire, we have to have a cross-section area that is going to be rectangular and with a width and height of 0.4, and the material is going to be steel, which is 2.6 times 10 power 5. So this one is in megapascal. However, because we are using a meter SI system, we have to transfer this one to Pascal, that I'm going to show you in Abaqus. Now let's start making this in Abaqus. Okay, similar to previous example, I'll start in a part section by creating a part, and from here so I have a 3D, or I can use 2D. In this case I'm gonna keep it as 3D deformable wire, and I'm going to use a planer, and for approximate size, because I'm using a meter unit system, I want this one to be 20, so that's which represents 20 meter. Okay, click on continue. Next step is to create our simple geometry that we had, which is the wire. Before doing that, I will create some construction lines, and I'm going to fix these lines. Okay, so very important point about distributed load is that you have to know the location of the 0, 0 in Abaqus in comparison to your model. Obviously in Abaqus the 0, 0 point located in the middle. However, Abaqus is not forcing that 0, 0 point to be your start point. For instance, in CAD software you always have that 0, 0 start point that you can start from here, but as you can see here there is not a like a point or node to select that area. So that's why I created these construction lines, so I have that 0, 0 point in that area. Why I say this is important, because when you want to generate your distributed load that we had here, and when you create the equation, and for instance the equation will have, I'm going to show you, for instance the equation that we're going to have for this one, for instance, is minus 5,000 x plus 300,000. Okay, and this x value basically comes from the 0, 0 point. So if you don't actually know where is the 0, 0 point in comparison to your model, you're going to be in trouble. So to make this clear, I will first generate this one, and then I will show you another example that the start of my sketch will not gonna start in the 0, 0 point, to make this more clear for you and why it is important you actually know where is the location of the 0, 0 point in comparison to your model. Okay, so now let's start by drawing a line. So I'm going to use a line, and I'm going to select this point, and I'm going to go up to here, doesn't really matter where, and another one, and just draw one line up to the end, and from here to here. Okay, so once we are done with this, we can give a dimension from here to here, that should be 4 meter, from here to here, that should be 4, and from here to here, that's 10 meter, and from here to here again it's 10 meter. Okay, so what I want to do now, because as I said, you see that this one is not anymore located in the 0 point. So what I can do, I can use these coincident and select this point and this line, and as you can see now it's exactly located in the 0, 0 point. So now let's cancel this, click on done. So we have this geometry. So if you remember, we had a concentrated force here somewhere in this area. So I'm going to just show you in the slide. So this is like a 5 meter from this corner, and I can see that the length of this is 12. So let's just first quickly modify this. So I'm going to go here, click on this, go here, wire, double click on this one, and click on edit dimension, select this, make this one 12, and select this one, make this one 12 as well. As you can see, this is outside the sketch area, but this is, as I mentioned many times, this is just for a guide, and if your line or sketch is out of this area, it's not really affecting anything. So let's cancel this and go back to geometry. So once we are doing this, as you can see, there is a yellow box here. That means that yes, we have done a modification, but it's not applied yet. So what we need to do, we need to right click on this and regenerate this one, make it longer. Okay, so now let's go back to this one to create a partition. So when we want to create a partition, as you can see, this is a 5 meter from this corner, and we can actually do that very simply by going here and using a partition edge interparameter. And I can select this line and click on OK. But as you can see, the value is normalized. So basically said you have to put a value from 0 to 1. So it's kind of like a percentage thing. And this direction is important as well. So that means that this direction comes from left to right. So in order to find that percentage, we know the length of the R line, which is 12, and we know that this is 5 meter from this side. So if I simply divide 5 by 12, and that would give me the portion. So that's going to be, let's say, 0.41, or we can even say 0.42. And so if I say create partition, you see that that's located in this area. And if I'm happy with this, I can say done. And if I go on the line, you see that I have one line here, one line there. So later we will use this point that we created here to apply a load. Otherwise it's not really possible to apply a load. We can also use a mesh, the node created by mesh, but this is a more accurate way because we exactly know the location of the node that we created there. Okay, so now we are done with this. I'm going to go to property and create a material property for this section. Okay, so for material, as I said, we're going to make a still. So create material, at the top type still, and use mechanical, elasticity elastic, and for Young modulus use 2.1, and because we are using a meter, that should be in Pascal, so that is going to be E9. So that actually should be 210 E9. So because the still Young modulus is 210 gigapascal, and if I want to transfer a gigapascal to a pascal, I have to times that to 10 power 9. And for Poisson ratio, type 0.3 and click on OK. So we are done with this one, and now I have to create a section. So create a profile first, and we're going to use a rectangular. Click on continue, and let's say this is 0.4 and 0.4. Click on OK, and then we create a section for this one, and that's going to be beam, and we can call this one still section, and click on continue. And as you can see, so we have a profile here which is rectangular, we have a still as a material, and click on OK, and assign this one to the geometry and click on done. So we have this, and now I'm gonna assign a beam section. So select this one, select everything, click on OK, press enter, click on OK again, and if I go to view and part stack plot option, oh sorry, not this one, if I go to part display option and from render, if I apply this, you can see the 3D version of our bracket. So deactivate the render, click on apply, and next step is going to be assembly. So in assembly, I simply click on create instance, and I'm going to import it as a dependent, so it's going to be mesh on a part, and click on OK. We don't have to do anything else because we have just a single object. And next step is going to step, and we're going to create a step here. So it's going to be static general, and nonlinear can be off. Number of the increments 1000, make this one 0.1, and minimum element 15, and click on OK. Also from here we can go field output, as I showed you, where you can request a force on a nodal force in a beam section orientation, so you can request system to see the force on each individual section. So now the next step is going to be interaction. In interaction we don't have to do anything, and the next step, which is the most important part, and the aim of this tutorial, is going to be load, that you're going to learn how to apply a distributed load. Okay, now first let's just do the easy one. So let's fix these 3 sections and apply this concentrated load, and then we'll go to do the distributed one. So first we click on create boundary condition, and we go for the first one, and we select this one, hold the shift and select the other nodes, and click on OK, and we'll say that they are fixed, or we can actually say they are pinned. Click on OK, and the next step is to apply this concentrated force there. So I'm going to create a concentrated force, select on this one, click on OK, and the value was 10 kilonewton, and if you remember, we are using a SI, and regardless if it's a meter or millimeter, the unit of the force is always in newton. So if it's 10 kilonewton, so that should be 10,000 newton. So this is very important. Okay, click on, so that so it should be going down, so that is going to be negative, so I have to put a minus there. Click on OK. I have noticed that you might have to put a plus or negative, depends on the version that you're using. I think that in the newer version, when you put the plus value, it automatically apply a force in a compression. So if your arrow is in opposite direction, just adjust the sign behind the number. So we are done with this. Now we're going to apply a distributed load. So the first one is going to be a rectangular one that I'm going to apply to that line, and in order to do that, I'm going to use from here either pressure or line load, because here is a 2D wire, so we definitely can use a line load. The units of a line load are force per unit length, which is exactly what we have here. So as you can see, it's a 10 kilonewton per meter, and although we have to just change this one, obviously write it in a form of newton, so it's going to be 100,000 newton per meter. So let's go for a line load and click on continue, and select on this, click on OK, and so this is going to be 0, this is going to be 0, and this is going to be so no, this one is going to be 0, this one is going to be minus 100,000. So I'm going to just double check if it's in newton, yeah, and the sign should be positive actually, because the x is in the positive and I want my force to be in this direction. So click on OK. As you can see, we have a force. As I explained, the load section, the size of the arrow doesn't really say anything when you apply a uniform load. So as you can see here, this one represents 10,000 newton, and this one represents 100,000 newtons, but they are in the same size, so it doesn't really represent anything. However, when you do a distributed load, not uniform distributed load. For instance, let's imagine that we are doing the triangle one. Then in that case, Abaqus, the arrow size will change. So how we can actually do a distributed load in Abaqus when it's not uniform? In order to do that, again, I'm going to go to create load, and I'm going to go to line load and select the line, click on OK, and from here, as you can see on the side, we have create analytical field. And so if I click on this one, then I can select the expression field, and I can, from here I can actually generate the equation that I want to use for distributed load. How we can actually generate these equation? Sometimes in some examples you would have actually that distributed load equation, but in this case that we don't have, we can actually generate that using a Excel file. So if I go to Excel, I know that if I consider this one is a 0, 0 point, I know that at 0 the load is 300, and at 4 meter the load is 100. So what we can do, we can say 0 equals to 300, and when it's 4, that equals to 100, and I can generate a line like this. So, and you have to just be careful that Excel is selecting a correct row. So in this case it hasn't, so I'm going to just change this one. So I want my x-axis to be this, and my y-axis to be this one, and click on OK. So this is the line that is going to have for that formula. So I'm going to just, so this is basically going to be x, and this is going to be y, and that's force, and that's basically distance. And what we want to do, we want to basically create an equation that represents this line, and we can simply do that by right click on this, add a trend line, and display equation. So we have this equation here. However, this is the equation for when it's kilonewtons, so I'm going to add 30 for each of these. So that's going to be 300, and this is going to be okay. So that's going to be the equation that I need to use for my in Abaqus. So I'm going to copy this one and go to Abaqus and paste it here. So I did that simply by using a Ctrl V in the keyboard. Okay, and so now I have this formula, but as you can see in the example, Abaqus doesn't really understand when you put a number and the alphabet immediately, so you have to put a mathematical sign here. So if it's a time, so I'm going to use this one, star, and from here instead of x I have to use y, because the distance for my case is going from 0 to y. So this is like a 0 to 4 millimeters. So instead of x, I'm going to get rid of this x, and I'm going to make this one y. Okay, so when I have so this basically, this equation says that when I have a my y as 0, that I'm going to have 300,000, and when y become 4, so that's going to be 4 times 50,000, so that's going to be 200,000 minus, and plus 300,000, that's going to be 100,000 positive. Okay, so this is the equation that will represent these distributed load in this example. So if I click on OK, from here I can change this one to analytical field, and I'm going to make this one 0, I'm going to this one 0, and this one 1. So why 1? Because I actually don't have to apply a load here, because these analytical fields will generate that force based on the distance. So if I click on OK, you'll see that here I have 300,000 and here I have 100,000. Again, as I said, don't worry that this arrow is bigger than the other arrow. They basically, these two forces are equal to each other, so this is 100,000 and this is 100,000. But Abaqus again doesn't generate the arrow based on the size of the force that you apply. So these are, it doesn't matter what load you apply, the size of the arrow is going to stay as it is. And again, in a distributed load, in a non-uniform distributed load, it doesn't really matter what is a maximum and minimum, you're going to have exactly the same order. So don't worry about the size of the arrows. So now we are done with applying a distributed load. I'm going to go to mesh section part because it's dependent and apply a 4, and let's just apply this one. So this is, I think it's a little bit too coarse. I'm going to make this one 0.5. Apply. This is a fine. Okay, click on OK. Assign a mesh. Say yes. Then go to job, and what I'm going to do, I'm going to create a let's say I'm going to call it bracket to the wire, and continue, click on OK, and I'm going to submit a job. And if there is not any problem, I shouldn't get any error, can monitor that. So no error, but this should be a very quick simulation as well. As you can see, it's done after 6 increments, and just look at the result. And as you can see, this is going to be the displacement that we this is a stress that we have, and we can also see the displacement as well. So from here we can actually see the so as you can see, Abaqus is exaggerated the displacement that we have. If I put it on uniform and if I say 1, you see that we don't have that big displacement. It's just a exaggeration, so you will have a better visualization of the displacement in your bracket. Also, you can activate from here render a beam, so you can actually see this one in 3D. Okay,